So you know that we have certain variables, certain decision variables for which we want the solution to be optimized, the profits to be maximized, or the cost to be minimized. So we actually studied, we discussed about two kinds of processes to solve certain problems. The first one was the graphical method, and the second one was simplex method. So in graphical method, what we do actually is that when we have only two variables, then we go for the graphical method. But if there are two or more than two variables, it also includes two. But if we have two or more than two, then we go for the simplex method. So the simplex method is actually the algebraic solution to the optimization problem. First, we discussed and we studied was the graphical solution that included two variables. But when we go to the algebraic solution of the optimization problem, then it becomes the simplex problem. So in simplex, what we do actually is it has a certain structure to write the equation. We have to add some additional variables in it, and then we have to go through an iterative process. This is simplex method is actually an iterative process. It does not, solve the problem in just one step. You have to repeat the steps, and you keep getting some feasible solution. And at the end, when certain points are met, when certain conditions are met, you come to know that now this is the final solution. We will discuss what are the conditions to be met and what are the situations that we follow once we start the actual simplex problems and we start solving it. So there are two conditions that we must have in the simplex problem. The first one is that it must be a maximization problem. That is must. The first thing that we need to do is that we must have the problem in maximization form. It should not be in minimization form. And secondly, all the constraints must be less than or equal to some constants, for example, Ci. It must be in the less than or equal to form. Are you getting the point? Yes. Okay, we have two conditions. It means that, for example, we have a problem like maximum z is equal to 2x1 plus 3x2 and subject to 2x1 plus x2 less than or equal to 4, and the second constraint is x1 plus 2x2 less than or equal to 5. You see that both the constraints are less than or equal to. Do you see it? This should be the case. This should be the case when we do simplex. Whenever we do simplex model, first of all, it should be a maximization problem. It should not be a minimization problem. If it is a minimization problem, we need to convert it to a maximization process and that process we will study later on. But just need to know that the simplex method has two main points. The first thing is that it should be a maximization problem. The second one is that all the constraints must have less than or equal to sign. It should not be greater than or equal to. If it is greater than or equal to, we need to convert it into less than or equal to and then proceed towards the simplex method. But those things we will discuss later on. Okay. Now you see what I meant by these two conditions. Yes. So these are the two conditions for the simplex method, to work out. If these conditions are not met, then we cannot proceed towards the simplex method. We need to have both these conditions met. Now, when we have in simplex method, we use some slack variables to add it to the constraints and the objective function. So there is a defined method to write the question in simplex form. The method or the procedure, I will write it down here to show you how we write the simplex questions. So we have an artificial variable, and you can say it a slack variable. There are two things. One is slack, and the other is surplus variables. Slack variable and surplus variable. These two are the kinds of variables that we introduce into the simplex method. But when we have maximization problem and these conditions met, we only introduce the slack variable. For example, in the above question, the first constraint C1 is 2x1 plus x2 is less than or equal to 4. So now when we equate it in graphical, we equate it, but we do not add any kind of artificial or slack variable. But in the simplex, we add an artificial slack variable to it. We write it as follows: x2 plus s1 is equal to 4. This s1 is actually the slack variable. This is the amount by which the right hand side, it is more than the left hand side. If we add this one to the left hand side, it equates to the right hand side. The what I can write, for example, we say that 2 plus x is equal to 7. Okay, or we write it as follows, like for example, 2 plus x is less than or equal to 7. Now this x is the slack that the right hand side, that the left hand side is lagging. The left hand side is actually x quantity lesser than 7. So if we add, for example, 5 to it, it becomes equal to the right hand side. So 5 here is the slack constant. But here we use variables. We do not, use constant, because we have to find the value for these slack variables. This was just for example. This is not included in here, but it was just, to make you understand the process. You see how we add the slack variables to the constraints? Okay. So now we have a standardized form, a standard form to write simplex equations or simplex problem. The first thing is maximum z is equal to 2x1 plus 3x2 minus 0s1 minus 0s2. We use only two. Yes. This was just to make you understand. For example, we write, this is constant. That is why I chose this specific scenario to make you understand. But for example, uh, there are two brothers. Okay, there are two brothers, and both of them differ by 5 years. The elder brother is 5 years elder to the smaller one. So what will you do to make them equate their ages? For example, you have to equate them. What will you do? You have to add some age to the smaller one in order to equate it to the elder one. For example, I am 5 years older than you. Like for example, we write that this constraint like 2x1 plus x2 is less than or equal to 4. Now this less than or in this one, yes, actually I wrote this one first. For example, 2 plus x is less than or equal to 7. So what will be the value of the x, to equate it to 7? So we add 5. We add 5 to the 2 to make it equate to 7. So this 5 is actually the slack variable. 2 was, 5 units smaller than 7. Let me make you understand this in constraint, in this practical constraint. Look, 2x1 plus x2, this this is left hand side of the equation, okay, of the inequality, and therefore this one is the right hand side. Now what does this inequality says? This inequality says that the left hand side is smaller than or equal to the right hand side. Now to equate the left hand side to right hand side, we need to add something to the left hand side in order to equate it to the right hand side. For example, there is a balance. There is a balance with what we weigh things. the vegetables or fish or anything like that. Okay. On one side, we put weight of like 5 kgs. Now that side is greater than the other side. The other side is lighter. Now we have to add 5 kgs to the other side in order to equate them both. Now you understand? Okay, so the surplus, the slack variable is when the constraints are in less than or equal to form. Just remember this thing. You can write it down. You can write down these two conditions, and you can write down the that we add slack variable to these kind of constraints which are less than or equal to. Now, the standard form is we we have two constraints over here, constraint number 1 and constraint number 2. So we can only add two slack variables here. So the coefficient of slack variables in the objective function is 0. Okay. Now subject to 2x1 plus x2. Now we need to add s1 and it will be equal to 4. Similarly, x1 plus 2x2 plus s2 is equal to 5. So this is the and x1, x2, s1, s2. They are all greater than or equal to 0, which is the non-negative constraint, and we need to write it with every kind of linear problem. So now this is the standard form of writing the simplex model. Now, when we solve the simplex problems, it is actually an iterative process. Iterative in a form that you cannot go to a solution in just one step, but you have to repeat the steps in order to you have to repeat the step. It is iterative process. Iterative process means that you have to repeat the algorithm again and again to come to the optimal solution. So simplex is actually an iterative process. Now each iteration have certain steps that we need to follow in order to come to the solution. We need to write the those certain steps. For example, uh, should I solve the same problem that I wrote over here? Yes. We have maximum z is equal to 2x1 plus x1 plus 3x2 plus 0x1 plus 0x2 subject to 2x1 plus x2 plus s1 equal to 4 and x1 plus 2x2 plus, you can write here 0 s1 or you just have to write s2 equal to 5. Now we write it into a form standard form of a table in tabular form, and then we will proceed towards the main procedure of it. The standard form is like this: is the basic variable. Here we can write z and the number of slack variables that we have. Then we write over here is z. Yes, yes, we add it to constraints. We do not add it to the objective function, but we add it to the constraints actually. Yes. For example, the constant 1 is there, so it will have one slack variable, and that will be named as S1 because it is the slack variable for constant 1. In constant 2, we will have only one slack variable, and that will be S2 because it is linked to the constant 2. And if we have constant 3, then we have the third slack variable, and that will be named as S3. And that will be added to the respective constraints only. That will not be added to all of the constraints. In other constraints, for example, we have constraint 1. So in this constraint, only the coefficient of slack variable s1 will be 1. Without s2, s3, s4, all of them will have like 0 coefficient. So we actually ignore it. We do not write it. In constraint 2, only the coefficient of S2 slack variable will be 1. The slack variable 1 coefficient will be 0, the S3 will be 0, and S4 will also will be 0. So we ignore it, and we do not write it. Okay. So this basic variable, we write Z S1 and S2. And here we write Z X1, X2. How many variables are there? There are two variables, X1 and X2. And also we have slack variables, S1 and S2. And then we write solution. And then we write a ratio. And ratio is solution divided by pivot. I will explain the pivot and all the terms, but you just need to write it just like I wrote it over here. Okay. So now reading the above equation, convert this one into a form like this: z minus, here we have equal to sign, so this equation will it will move to this side. So we will get z minus 2x1 minus 3x2 minus 0s1 minus 0s2. Now the coefficient for z here is 1, so we will write over here is 1. The coefficient of x1 here is minus 2, so we will write here is minus 2. The coefficient for x2 is minus 3, we will write minus 3. For S1 it is 0, for S2 is 0, and the solution is 0. So the initial solution will be 0. Now we need to write same for the constraint 1 and constraint 2 over here, like we just wrote for the maximization function. For S1 we have z is equal to 0. The coefficient for x1 in constraint 1 is 2. For the coefficient of x2 for S1 constraint 1, it will be 1. S1 is also 1, S2 is equal to 0, and the solution is equal to 4. The right hand side is equal to, you can write here is right hand side or solution. Okay. Similarly for S2, the second constraint, we can write it. The z is 0, the x1 is 1, the x2 coefficient is 2, S1 is 0, S2 is 1, and the solution is 5. Now we start the first iteration towards solving this problem. Okay. So now, first of all, we need to find the ratio. The ratio will be, first of all, we need to define the entering variable. Now, as it is maximization problem, the entering variable will be the most negative of all in the 0. So -3 is the most negative one. So x2 will enter. Now we need to find out which variable to get out of the equation. X2 will enter here, and among S1 and S2, one of them, it will be eliminated. So we need to find out which one to be eliminated. Now we found out that the x2 is the entering variable. X2 is entering variable. For this, we need to find the ratios. To find the ratio, we need to divide the right hand side with the coefficient of the entering variable in the entering variable column. Now here the solution is 0, and the entering variable column coefficient is -3. Here we have 4 by 1. Here we have 5 by 2, which is equal to 2.5, 4, and this will be negative. We must ignore zeros and negatives in here. We just need to find out the minimum positive. So the minimum positive is 2.5. So S2 will be leaving the system because it has the minimum ratio. Now we need to, this is our pivot row, and this 2 is actually the pivot element. Pivot element is equal to 2, because if we cross the pivot column with pivot row, 2 is on the intersection. So this one is the pivot element. Now what we will do is, in the next iteration, we need to make this pivot element as 1. We need to do the row operations, and we need to convert this one into 1 and above and below the pivot element, we need to convert all of them into zeros. We need to convert -3 into 0, we need to convert 1 into 0, and we need to convert this 2 into 1. For this, we do the row operation. Now we will do the row operation. So the row operations will be, first of all, we need to do the row operation for the pivot row. So new pivot row is equal to old row divided by the pivot element. Now the old row is 0, 1, 2, 0, 1, and 5 divided by 2. What we will get? 0 by 2, 1 by 2, 2 by 2, 0 by 2, 1 by 2, and 5 by 2. We will get 0, 1 by 2, 1, 0, 1 by 2, and 2.5. So this is the new pivot row. Are you understanding the process? Okay, now after defining the new pivot row, we need to convert all the rows in accordance with the new pivot row. And as I defined, we need to convert -3 into 0 and 1 into 0. And we already converted this 2 into 1, as the new pivot row is this one. So we need to write again this question into this tabular form. Now defining the next table, we have basic variable. So we were here and we found the new pivot row. The new pivot row was for z it was 0, for x1 it was 1 over 2, for x2 it was 1, because we need to, because x2 was entering variable, so we need to make it 1, and earlier it was 2, so we need to make it 1. And for x2 for s1 it was 0, for s2 it is 1 over 2, and the right hand side solution is now 2.5 for x2. Now we will make new rows, new z row and new s1 row, and then we will put these values and make the second iteration. So now the new 0 will be is equal to old 0 minus the pivot column coefficient into new pivot row. So this is the equation. The new 0 will be equal to old 0 minus pivot column coefficient into pivot row. So now the new 0 is equal to, the old 0 is equal to 1 minus 2 minus 3, 0, 0, and 0, minus the pivot column coefficient for this row is -3. -3 into pivot row, new pivot row is equal to 0, 1 over 2, 1, 0, 1 over 2, and 2.5. So now we get 1 minus 2 minus 3, 0, 0, 0. So it will become minus into minus, it will become plus. So when we multiply it, we get 3 into 0, 0, 3 by 2, 3, 0, 3 by 2, and 3 into 2.5 is equal to 7.5, which becomes 1 plus 0 becomes 1 minus 2 plus 3 by 2 minus 2 plus 3 by 2 minus 3 plus 3 is equal to 0. 0 plus 0 is equal to 0. 0 plus 3 by 2 is equal to 3 by 2. And 0 plus 7.5 is 7.5. This will become minus 2 plus 3 by 2. It will become minus 0.5 or minus 1 over 2, 0, 0, 3 by 2, and 7.5. Now we put, this is the 0. We can also write it as z star 1 because it is the first iteration of the zth row. So we now put this value over here in this new z column. This z column will become 1. X1 is minus 1 over 2. X2 is 0. S1 is 0. S2 is 3 by 2. And the right hand side is 7.5. Now the S1, new S1, the S1 new or star will be equal to the old S1 row minus pivot column coefficient of that row into new pivot row. Remember that we need to make the key element or the pivot element 1, and the above or below these in the pivot column, we need to make it 0. So now in the 0, the x2 is now 0. Similarly, now for the x2 in the S1 ratio, S1 column, we need to make it 0 here too. So the old S1 is 0, 2, 1, 1, 0, and 4 minus the pivot column coefficient for this row is 1. So 1 into the new pivot row is 0, 1 over 2, 1, 0, 1 over 2, and 2.5. So it will become 0 minus 0, 2 minus 1 over 2, 1 minus 1, 1 minus 0, 0 minus 1 over 2, and 4 minus 2.5. So we get here is 0. This will become 1.5, which is also 3 by 2, 0. 1 minus 0 is 1. 0 minus 1 over 2 is minus 1 over 2. And 4 minus 2.5 is 1.5. So this is the S1 star, the new S1 row. So we will put these values over here, and we will get is 0, 3 by 2, 0, 1, minus 1 over 2, and right side here is 1.5. Now we will take over the next iteration from here. Now we see that we decided to select the entering variable as the most negative one here. Now here the most negative is x1, which is minus 1 over 2. This is the most negative one. So here now x1 is the entering variable, and we have to we know automatically that now s1 is the leaving variable, but let's find the ratios and define the leaving variable just as a process, but we know that s1 is the leaving variable. Now the ratio for this will be, the right hand side is 7.5 divided by the pivot element is, here is minus 1 by 2 or minus 0.5. Here it is 1.5 divided by 3 by 2 or 1.5, which is equal to 1. And here it is 2.5 divided by 0.5. I don't know what it will become, but let me calculate it. 7.5 divided by 0.5. It is minus 15. As it is negative, so we will ignore it. So this is to be ignored because it is 0. Because it is negative. Negatives and zeros are meant to be ignored. Now we have 1 over here, and the other one we get is, I guess it will be like somewhat 4 or something divided by 0.5. 5. Now the minimum is this one. So S1 here is the leaving variable, and X1 is the entering variable. Now we will update this table. We update this table over here. We write basic variable, v x1, x2, s1, s2, the right hand side or solution, and ratio. Now here we have z. We will replace s1 with the x1, and we have already x2 over here. This will enter into the system, and s1 will leave the system. Okay. So now we need to update the pivot row, because pivot row is this one, and 3 by 2 is the pivot key element. Okay. So now we need to update all these rows and get the final solution. And I will also show you what is the condition for us to know that the final solution has arrived, and it is not even more possible to continue. So now the z here is z x1, x2, s1, s2, right hand side, and ratio. So first of all, we will update the new pivot row. So the new pivot row will be equal to old pivot row divided by the pivot element. Now the pivot element here is 3 by 2. So the old one is 0, 3 by 2, 0, 1, minus 1 over 2, and 1.5. And we divided it by 3 by 2. So what we get is 0, 1, 0, 1 divided by 3 by 2 is 2 by 3, and 1 by 2 divided by 3 by 2 is minus 1 by 3, and 3 by 2 divided by 3 by 2 is 1. So this is the new pivot row. So update the new pivot row over here. What we get is 0, 1, 0, 2 by 3 minus 1 over 3, and the right hand side we get 1. Are you understanding the process? It is 107. This is page number 107. Yes, the Hamdi Taha. Because the simplex method, this is yes. This is for a simplex method. Yes. This is for this is an iterative method. Yes, this is iteration based method. The graphical method was not iterative based. It was like on spot. You need to get some feasible solutions, 3 or 4 feasible solution, and an intersection of them we got like one optimal solution. But here, this is the second iteration. Yes, and it will not be lengthy in the exam. The exam, the teacher will, the instructor will give you questions like which can end up into like at most 3 iterations, not more than that. Yes. So that is why I chose like a smaller question, but yet I want you to know about the whole process of it, and think about the small bits of it to understand it. Like yes, I will solve like 2 more examples inshallah today. One will be for the maximization problem, while the other will be the minimization, but we will convert it into maximization and then solve it. Because in an exam you can have like a minimization problem, but you will have to convert it into maximization, and the teacher can trick you in these kind of things. Because in simplex method you will have to convert every minimization problem into maximization and then solve it. You cannot solve minimization at itself. Yes. So now this is the new pivot row. The new pivot row is updated over here. Now from this new pivot row, we need to make the coefficient for x1 in zeros and the coefficient for x1 in the x2 row to be 0 and 0. How we will do it? We will do it using the row operation. Now the first row operation will be finding the z double star. By double star, I mean this is the second iteration for z to change, or the new 0. Okay, so it will be equal to old z star row minus pivot column coefficient into new pivot row. Now the old 0 is The old 0 is 1 minus 1 over 2, 0, 0, 3 by 2, and 7.5. Now, the pivot column coefficient for this row is minus 1 over 2 into the new pivot row is 0, 1, 0, 2 by 3 minus 1 over 3 and 1. Now we get the new z or z double star is 1 minus 1 over 2, 0, 0, 3 by 2 and 7.5 minus 0, 0, 1 over 2, 0, 1 over 3, 1 over 6, 1 over 2. We will get is 1 minus 1 plus 0 is 1, minus 1 over 2 plus 1 over 2 is 0, 0 plus 0 is 0, 0 plus 1 over 3 is 1 over 3, 2 by 3 plus 1 over 6, 3 by 2 plus 1 over 6 is we get here 1.66 and 7.5 plus 1 over 2 is 8. This is the 0. This is the new 0. Now we need to find out the new. We will update this 0 over there, which is 1, 0, 0, 1 over 3, 1.66, and 8. And the new x2 ratio, new x2 row is equal to old x2 row minus pivot column coefficient into new pivot row. Now the old x2 row is 0, 1 over 2, 1, 0, borrow 1 by 2 and 2.5 minus 1 over 2 into 0, 1, 0, 2 by 3 minus 1 over 3 and 1. What we will get here is 0, 1 over 2, 1, 0, 1 over 2, 2.5 minus 1 over 2 into 0 is 0, 1 over 2 into 1 is 1 over 2, 0, 1 over 2 into 2 by 3 is 2 by 6, which is 1 over 3, and 1 over 2 into minus 1 over 3 is minus 1 over 6 and 1 over 2. What we get is 0 minus 0 is 0, 0 minus 1 by 2 minus 1 by 2 is 0, 1 minus 0 is 1, 0 minus 1 over 3 is minus 1 over 3, 1 over 2 plus 1 over 6 is 2 plus 1 over 6 is 2 by 3, and 2.5 plus 0.5 is 3. So this is the x2 new. Now we update this over here, which is 0, 0, 1 minus 1 over 3. 0, 0, 0, 1, 0, 0, 1 minus 1 over 3, 2 by 3 and 3. Now, we have now a terminating condition that is met over here. We see that in the z column, in the 0, there is no negative element. But in maximization problem, when we come to a point that we do not have negative element in z row, we know that the optimal solution has arrived. Now, what is the optimal solution? The optimal solution is z is equal to the right hand side, which is equal to 8. So 8 is the maximum profit that we achieve here. And x1 is equal to 1 and x2 is equal to 3. For x1 row, we see that the right hand side is equal to 1. And for x2 row, we see that the right hand side is equal to 3. So the optimal solution here is x1, x2 is equal to 1 and 3. And z maximum is equal to 8. That is the optimal solution here. Now you understand about the terminating condition. Yes. I am now going towards another maximization problem, and after that I will do a minimization problem, and we will convert it to maximization first, and then we will go through it using the same procedure. And inshallah, in the next lecture, we will go to the big M method, and we will also do the Torah tutorial for 1 or 2 questions. Maybe yes, inshallah, maybe the question that I solved today, I will put same data in the Torah, and we will, compare the results of it. Inshallah. So yeah, this is the case over here. So we have arrived to an optimal solution for which z is equal to 8 and x1, x2 is equal to 1 and 3. So this is the simplex method. Now we see, a bit more complex problem than this one. Okay, and I will solve the question with using the same procedure. We will repeat it, and inshallah after that I will do a minimization problem. Okay, so now moving to the second maximization example. Okay, so we have the objective function is maximize z is equal to 5x1 plus 4x2 subject to 6x1 plus 4x2 less than or equal to 24, while x1 plus 2x2 less than or equal to 6. Yes, the reference for this is page number 106. The earlier was on 103, 102 and 103. The third constraint is minus x1 plus x2 less than or equal to 1. The fourth one is x2 less than or equal to 2. While, so now, first of all, the first thing that we do here is to convert it into the typical simplex W. Okay, the simplex W, we write it as the basic variable z x1. We have two variables over here, and we have like 1, 2, 3, and 4. 4 constant, so we will have like 4 slack variables for these S3 and S4. This is the right hand side, and then the ratio. Okay, and here we will write the slack variables. Should I transform this form to the standard one, or should I leave it? You understand it. Yes, yes, we have to do the slack variables. Should I go to the W, or should I make this one first and then go to W? Okay, I will make side by side. Okay. Now we have 4 slack variables over here. The first constraint, we have the slack variable of S1, which is 6x1 plus 4x2 plus S1 is equal to 24. The second one is x1 plus 2x2 plus S2 is equal to 6. The third one is minus x1 plus x2 plus S3 is equal to 1. And the fourth one is x2 plus S4 is equal to 2. And in accordance to it, we will have the maximization function as z minus 5. Okay, so you have this this W, and we will now update it according to the objective function and the standard mathematical model for the simplex. Now, in the problem, we have z is equal to 1 in the objective function, x1 is minus 5, x2 is minus 4, s1 is 0, s2 0, 3 0, 4 0, and right hand side is also 0. Now for s1, the constant one, we have z1 is equal to 0 in all those 4. So we will write 0 below this z column for s1, s2, s3, and 4. For s1, in constant 1, x1 is 6, x2 is 4. For constant 2, x1 is 1 and x2 is 2. For constant 3, x1 is minus 1 and x2 is 1. For constant 4, we have x1 is equal to 0 and x2 is equal to 1. Now, we have a certain order over here. For constant 1, s1 will be 1 and all other will be zeros. For constant 2, the s1 will be 0, s2 will be 1 and s3, s4 zeros as well. So for constant 3, we have 0, 0, 1 and 0. For constant 4, we have 0, 0, 0 and 1. We have this kind of identity column over here. For the right hand side, we have for constant 1 is equal to 24. For constant 2, we have 6. For constant 3, we have 1. And for constant 4, we have 2. Now, what we need to find is, we need to find the pivot column. That is the entering variable. For entering variable in maximization problem, we need to find out the maximum negative value in the 0. This is the 0 and minus 5, which is under the x1 column. This is the highest negative value. So x1 here is the entering variable. So x1 is deemed as the entering variable. Now we also need to find out the leaving variable. It must be one of the slacks. One of the slacks will leave the system and we have to find it. We need to find it using the ratio column. Now, in the pivot column that we introduced as x1, we need to divide the right hand side for each of the row by the coefficient of the x1 column. Okay, so the ratio here will be 0 divided by minus 5. Here it will be 24 divided by 6. Here it will be 6 divided by 1. Here it will be minus 1 divided by 1 divided by minus 1. And here it will be 2 divided by 0, which is equal to infinity, minus 1, 6, 4, and minus 5. Here is a rule over here. We must ignore, in the ratio column, we must ignore zeros, negatives, and infinity. Okay, we'll just look for the positive ones, and the least positive one is the row that we choose and that has to escape the system. So now here in the first 0, it is minus 5. So it cannot leave the system. This is to be ignored. We have 24 over 6 is equal to 4 and 6 by 1 is equal to 6. So the minimum one is 4 and it comes as that S1 will leave the system. So S1 is the leaving variable is S. Now we need to find the new pivot row, the new pivot row and pivot element. The pivot element will be the intersection of the pivot row and pivot column. This is x1, this is the pivot column, and s1, this is the pivot row. So 6 is the pivot element. So pivot element is is 6. Now, the new pivot row is equal to old pivot row divided by the pivot element. Pivot element is 6 and the old pivot row is 0, 6, 4, 1, 0, 0, 0 and 24. We need to divide it by 6. So we get 0, 1, this is 2 by 3, 1 over 6, 0, 0, 0, and here we get 4. So this is the new pivot row. So now we have to update the simplex W. The simplex W is written as basic variable z x1, x2, s1, s2, s3, s4, right hand side, and overhead ratio. And here is s1, 1 by x1, because x1 entered system and the system. And here it will be s2, 3, and pivot row is 0, 1, 2 by 1 over 6, 0, 0, 0, 4. Okay. So now, after finding this new pivot row, we need to do the row operations, and we need to find the new 0, the new S2 row, the new S3 row, and the new S4 row using the row operations. And the row operation can be defined as new 0 or Z star is equal to old Z minus pivot element coefficient, pivot column coefficient into the new pivot row. Actually, you have to make this one as 1 as we did here in the new pivot row, and all above and below these as 0, 0, zeros. So you need to make all of these as 0, 0, and 0, and it will be done using the row operations. So that is how we do it. So the new Z will be Z star is equal to the old Z, and the old Z is 1 minus 5 minus 4, 0, 0, 0, 0, and 0, and minus the pivot coefficient for this is minus 5. So minus 5 into the new pivot row. New pivot row is 0, 1, 2 by 3, 1 over 6, 0, 0, 0, and 4. So what we get over here is 1 minus 5 minus 4, 0, 0, 0, 0, 0. Minus into minus, it will become plus. So plus, and we have over here 5 multiplied by 0, we get 0. 5 into 1, we get 5. 5 into 2 by 3 is 10 by 3, which becomes like 3.33 or something. 5 into 1 over 6 is 5 by 6. 5, 0 into 0, 0 into 0, 0 into 0, and 5 into 4 is 20. Now, 1 plus 0 is 1. Minus 5 plus 5 is 0. Minus 4 plus 10 by 3. Minus 4 plus 10 by 3 is which is minus 2 by 3. Now 0 plus 5 by 6 is 5 by 6. 0, 0, 0, 0 plus 20 is 20. So this is the new z. Now we update this z over in this column, in this row. This is 1, 0, minus 2 by 3, 5 by 6, 0, 0, 0, and right hand side is 20. So the new updated solution in the first iteration is 20. But maybe this is not enough because we are getting a negative value over here. And whenever we get a negative value over here or anywhere in this 0, it means that the optimal solution has not arrived yet. So this 20 is not the optimal solution. It is feasible solution. It is one of the solution, but it is not optimal solution. So I hope that we can go for another iteration and then the optimal solution will be arrived and we will see the condition that all of these values are positive. So when these values in the z row is all of these are positives, it means that the optimal solution is arrived. So now we will update all the S2, S3 and S4 rows. So the new S2 star row is equal to the old one minus the pivot coefficient into the new pivot row. So the old S2 is 0, 1, 2, 0, 1, 0, 0, and 6. And the pivot coefficient for this is 1. So it will be minus 1 into the new pivot row is 1, 0, 1, 2 by 3, 1 over 6, 0, 0, 0, and 4. So what we will get over here is 0, 1, 2, 0, 1, 0, 0, 6 minus 1 into 0 is 0. 1 into 1 is 1. 1 into 2 by 3 is 2 by 3, 1 by 6, 0, 0, 0, and 4. So here 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 2 by 3 is 1.33. Okay. 0 minus 1 over 6 is minus 1 over 6. And 1 minus 0 is 0. 1, sorry. 1 minus 0 is 1. And 0 minus 0, 0 minus 0. And 6 minus 4 is 2. So we need to update the S2 row over here. So over here, it will be equal to 0. We already stated that it will become 0. Then in the X2 column, it will be 1.33 minus 1.6, 1 over 6, 1, 0, 0, and 2. So this is the new updated S2 row. Now, in the same procedure, doing the same procedure, we need to update the S3 and S4 row. Now, the new updated S3 row is equal to the old S3 minus pivot coefficient into new pivot row. So it will be equal to the old S3 is 0, minus 1, 1, 0, 0, 1, 0, and 1 minus the pivot coefficient over for the S3 is minus 1. We see here that the pivot coefficient for S3 row is minus 1. So we will put this coefficient over here, and then multiply it with the updated pivot row. The updated pivot row is 0, 1, 2 by 3, 1 over 6, 0, 0, 0, and 4. So doing this row operation, we get the new updated S3 row as follows. These negative and negative will multiply to get a positive. So both of these rows will be added. After addition, we will get 0 minus 1, 1, 0, 0, 1, 0, 1, and plus the new updated is 0, 1, 2 by 3, 1 by 6, 0, 1, 2 by 3, 1 by 6, 0, 0, 0, and 4. Solution over here is 0 plus 0 is 0, minus 1 plus 1 is also 0. 1 plus 2 by 3 is 1 plus 2 by 3 is equal to 1.666. Now 0 plus 1 over 6 is 1 over 6. 0 plus 0 is 0. 1 plus 0 is 1. The new updated S3 row is here, and we need to update this S3 row in the W. In the W, it is 0, 0, 1.666, 1 over 6, 0, 1, 0, 5, 1 over 6, 0, 1, 0, and 5. Now, in the same method, we need to update the S4. Now, S4 is equal to old S4 minus pivot column coefficient into the new pivot row. So here the old S4 is 0, 0, 1, 0, 0, 0, 1, 2 minus pivot coefficient over here is 0, 0 into the new pivot. So it will automatically become 0, so it will remain the same. So whenever we have the pivot coefficient as 0, you don't need to do anything. You just copy this one into the next one, update it as same. It will remain same. So we update it here and it will remain same. 0, 0, 1, 0, 0, 0, 1, and okay, so this is the updated column. Now we see that here a negative element is here in x2 column. It means that the objective function is not yet maximized. We need to do another iteration to find the optimal solutions. this is a feasible solution here. 20 is a feasible solution, but it is not optimal. So you need to do another iteration. Now we will update this W into another iteration. So the entering variable, now the entering variable will be x2, and the leaving variable will be among s2, s3, and s4, and that is what we will now find out. Okay, so x2 is this one, is the pivot column. Okay, now we have the pivot column and we have the right hand side. So we find the ratios of the pivot column and the right hand side. Right hand side divided by the pivot column coefficients. And we see that the minimum positive ratio, and against that, whichever row is that, whether it is S2, S3, or S4, that will leave the system, which has the minimum positive ratio. Negatives, zeros, and infinities, all of them are ignored. Only the positive ones are taken, and the least positive is taken as the leaving variable. Now the entering variable is defined as x2 because it is the most negative one in the z row. Okay, so now we will find the 20 divided by minus 2 by 3. It will go to negative, so we ignore it. Okay, we ignore it in the z1. x1 cannot leave the system, but yet, we need to 4 divided by 2 by 3, it becomes like 6. Okay, now 2 divided by 1.33 and 5 divided by 1.666, and 2 divided by 1 is equal to 2. 5 divided by 1.666, it may be it gives us close to 3.0 something. Okay, now 2 divided by 1.33, it gives us 1.5. So now the least one is this one, 1.5. So now against this 1.5, the variable that we have is S2. So S2 will leave the system. Okay, X2 will enter and S2 will leave the system because it has the least positive ratio. Now doing one other iteration and we get the most optimal solution. Okay, so we will update the table on this page. We make the same W, that is the basic variable, Z, the first x1 entered. Now S2 will be replaced by x2 because x2 entered the system. Here we will get x1, x2, s1, s2. It will remain unchanged. Okay, s3, s4, right hand side or solution or ratio. Okay, and here we will be writing s3 and s4. So now x2 actually enters the system and s2 leaves the system according to the ratios. Now the pivot element over here is 1.33 because it is lying on the intersection of the pivot column and pivot row, which is x2 and s2. So 1.33 is the pivot element. So the next pivot element is 1.33. So now we will try to make 1.33 as 1. We will change it to 1, and above and below 1.33 we will need to change all the coefficients to 0 using the row operations. So first of all, we will make the new pivot row. Okay, so the x2 row this one, it will be updated because it is the pivot row. So the new pivot row is equal to old pivot divided by the pivot element. The pivot element is equal to 1.33 and the old pivot is old pivot row is 0, 0, 1.33 minus 1 by 6, 100, minus 1 over 6, 100, and 2. We divided it by 1.33. What we get is 0, 0, 1. This one was required for us. That was something that we wanted to achieve. Okay. Now minus 1 over 6 divided by 1.33, it will get us to 1 divided by 6 divided by 1.33 minus 0.125. 1 divided by 1.33, it will give us 0.7500, and 2 divided by 1.33, which is equal to 1 point. Yes, camera is open. Now you can see. Okay, it was open. I don't know, maybe some connectivity issues there, but it was okay. So now you understand this point. It is same point, but I repeated it like for a second iteration. The new pivot row is equal to old pivot divided by the pivot element. So now we will update this new pivot row over here in the x2 row. It will give us 0, 0, 1, 0.125, 0.75, 0, 0, and the right hand side will be 1.5. Now, according to this new pivot row, we need to update the 0, x1 row, s3 row, and s4 row. We need to update all of these again, and then we will reach to the optimal solution. First of all, we need to update the row 0. The z double asterisk, we mean that it is the second iteration, okay, is equal to old z minus the pivot coefficient into new pivot row. The old z in the first iteration we got was 10 minus 2 by 3, 10 minus 2 by 3, 5 by 6, 0, 0, 0, and 20 minus the pivot coefficient in this one is minus 2 by 3. So we will take minus 2 by 3 and multiply it with the new pivot row. The new pivot row is 0, 0, 1, minus 0.125, 0.75, 0, 0, and 1.5. We will get 0, new 0 by using this row operation. Minus and minus, it will multiply to get us a positive. So we will get 10 minus 2 by 3, 5 by 6, 0, 0, 0, and 20 plus 2 by 3 into 0 is 0. 2 by 3 into 0 is 0. 2 by 3 into 1 is 2 by 3. 2 by 3 into 0 0.125. I need to find out using calculator. 0.125 multiplied by 2 by 3. It is equal to minus 0.083. Similarly, we need to find 2 by 3 into 0.75. 0.75 multiplied by 2 by 3. It is equal to 0.5. And we get 0, 0, and 2 by 3 multiplied by 1.5. It will get us 1. So now 1 plus 0, it will become 1. 0 plus 0, 0. Minus 2 by 3 plus 2 by 3, it will become 0. 5 by 6 minus 0.083. 5 divided by 6 minus 0.083. We will get 0.75. 0 plus 0.5 is 0.5. 0 plus 0 is 0. 0 plus 0 is 0. And 20 plus 1 is 21. So now the new updated solution is 21. It improved by a single number. So now we will update this C into this new table that we constructed. So it is 1, 0, 0, 0.75, 0.5, 0, 0, and the right hand side becomes 21. Now, what we see is that in 0, we have no negative. It means that we have arrived to our optimal solution, and 21 is the optimal solution for this problem. But yet we need to update x1, s3, and s4 row to find out the values for x1 and x2. x2 is already 1.5, but we need to find the value for x1. Okay, so now the new x1 will be x1 double asterisk is equal to the old x1 row minus pivot coefficient into new pivot row. The old x1 row over here will be this one. 0, 1, 2 by 3, 1 by 4, 1 by 6, 0, 0, 0, 4. Okay. So now we just write it 0, 0, 1, 2 by 3, 1 over 6. 1 over 6, 0, 0, 0, and 4 minus into pivot coefficient over here is 2 by 3. So minus 2 by 3 into the new pivot row. The new pivot row is 0, 0, 1 minus 1.25, 0, 0, 1 minus 1.25, 0.75, 0, 0, 0.75, 0, 0, 1 point, and 5. This is the new pivot row. So we need to do is the new row operation. What we get here is 0, 1, 2 by 3, 1 over 6, 0, 0, 0, 4, minus 2 by 3 into 0 is 0, 0, 2 by 3, and 2 by 3 into 1.5 is minus 0.833, zero point 0.500, and 2 by 3 multiplied by 1.5, it gives us 1. So we get here is 0 minus 0 is 0, 1 minus 0 is 1, 2 by 3 minus 2 by 3 is 0, 1 by 6 minus 0.833, divided by 6 minus 8. We found the x1 pivot table. Okay, and now we will update this one into the new table. So the x1 table is 0101 minus 0.5, 0101 minus 0.5, 005, 0, 0, and 5. Now we will update S3 and S4. So for S3, we need to find the S3 star star is equal to old S3 minus pivot coefficient into mu pivot row. Now the old S3 is old S3 is 001.66, 1 over 6, 0105. So we will write down 001.66, 001.66, 1 over 6, 00, sorry, 1 over 6, 0105. This is the old one minus the pivot coefficient for this is 1.66. 1.66 into new pivot row. The new pivot row is 001 minus 1.25, 0.75, 001, and 1.5. So doing this row operation, we get the updated S3 row is 0, 0. This is also 0, Now 1.66 into 1.25 is equal to 2.075. One divided by 6 plus 2.05 is 2.216. Now 1.66 multiplied by 0.75 equal to 1. Equal to minus 0.1245. So now here 0.6 into 0 is equal to 0, equal to 1, and 0 is equal to 0, 0, 0.5 minus 1.5 is 3.5. So this is the updated. We updated this one S3 over here. So the S3 is 000 2.216 minus 0.124 103.5. Now we update the S4 one. So the S4 mean is equal to old S4 minus pivot coefficient into new pivot row. Now the old S4 can be written as 001 triple 001 triple 12 minus the pivot coefficient over here is 1 into 001 minus 1.25 0.75 00 and 1.5. So it will become 001 triple 012 minus 001 minus 1.25 0.75 00 and 1.5. So we will get 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 1.25 is 1.25, and 0 minus 0.75 is minus 0.75, and 0 minus 0 is 0, and 1 minus 0 is 1, and 2 minus 1.5 is 0.5. So we will update this S4 star into this W, and we get is 000 1.25 minus 0.7501 and 0.5. So now we see that in the 0, all the elements are positive. So it means that we have arrived to our optimal solution. So the optimal solution for this question is 21. 21 is the maximum profit that we get, and the x1 value is 5 and x2 value is 1.5. So this is the solution for this simplex model. After this, I just want to take 10 minutes more of you, and I will, make a minimization model. I will convert it into maximization, and then we can follow the same procedure for all of them. So I will just quote an example of the minimization problem, and I will convert it into a maximization, just for you to know about the process of it. Okay. So we have, for example, a minimization problem is, for example, we have a minimization problem. Okay. I will tell, just take like for maybe like 10 minutes or not more than that. Not more than 10 minutes. Just, yeah. For example, we have a minimization function is minimize z 2x1 minus 5x2 plus 3x3 subject to x1 plus 2x2 greater than or equal to 5 and x1 plus x3 less than or equal to 7 and x1 plus x2 less than or equal to 8. Now, in this model, first of all, this is not a maximization problem. So what will we do? We will convert it into maximization problem. And then this constraint is less than or equal to, this one is also less than or equal to, but this one, the first constraint C1, it is greater than or equal to, it is in the greater than or equal to shape. So this is not acceptable in the simplex model. So first of all, we will need to convert this model into a maximization model. So how will we maximize it? We can maximize or convert it into the minimization into a maximization problem by multiplying it with -1. For example, this is the minimize z is equal to 2x1 minus 5x2 plus 3x3. Now, in the same mode, this problem will be in maximization if we multiply the right hand side with -1. So -1 into 2x1 minus 5x2 plus 3x3. It will become minus 2x1 plus 5x2 minus 3x3. So this will become a maximization problem. The coefficient, the objective function will be converted as. Now, we also need to convert the first constraint. So the first constraint is x1 plus 2x2 greater than or equal to 5. It will become minus x1 minus 2x2 less than or equal to -5. So this is how the minimization problem is converted into maximization problem. And the rest, for example, the other one, x1 plus x3 is less than or equal to 7. So it is okay. You don't need to change it. The other one, x1 plus x2 less than or equal to 8. This one is also okay. So you don't need to change it. And then you can write the basic variable and all that. And you can, we have like three constraints. So we have three slack variables, s1, s2, and s3, right hand side, and ratio. And here will we have sx, s1, s2, and s3. And we can write it down like this is equal to 1, x1 is 2, this is -5, and this is 3. S1 is 0, S2 is 0, S3 is 0. And similarly, we can, we can make the W and we can do the same process. Do you understand this process? We just, yeah, just we need, yes, we just need to convert the sign into smaller than or equal to and convert the minimization objective function into maximization 1 by multiplying it with -1. And we need to construct the same table and make the same procedure, same method. You don't need to do any extra part in it. You just have to be, consistent with the same algorithm, the simplex one. So this is all for today. Inshallah, in the next lecture, I will download today, inshallah, the Torah program. I will do some problems on Torah, and then we will compare the results in the next lecture for the problem that we solved today. So we will, check side by side how does the Torah work and how does the simplex work, and then we will go towards the big M method and the other one, what is it called, the two-phase method. Okay. Yes. Okay. Okay. Thank you. Thank you. You're welcome.